When most people interact with artificial intelligence systems today, they assume they are talking to a digital brain, a mysterious black box that somehow reads, thinks, and decides all on its own. But strip away the sleek chat interfaces, and there is no synthetic consciousness inside. Modern AI is composed entirely of middle school arithmetic, executed at an unimaginable scale. The foundation starts with a simple number. Take a 7. On its own, the number 7 is effectively silent. It could represent $7, maybe 7 days, or 7 degrees. It tells you how much, but without context, it cannot tell you what. Now group that number with others into a specific ordered list, say an 8, a 2, and a 6. Suddenly, you have context. Those numbers can represent a movie's action, romance, and comedy ratings. The power of an artificial intelligence doesn't come from complex algorithms. It comes from organizing these basic numbers into a structured architecture called a vector. A vector is simply that ordered list of numbers. Because the list is ordered, every position corresponds to a consistent feature. In a data set of users, the first number is always their age, the second is their income, and the third is their monthly purchases. This diagram shows how those numbers translate directly into physical geometry. Each feature becomes an axis on a graph. Age forms the x-axis, income the y-axis, and purchases the z-axis. Our simple list of numbers is now a coordinate, pinpointing an exact location in space. This process of converting an object into a coordinate is called embedding. AI models map words, images, and movie genres into numerical coordinates, populating the entire grid with information. Once the space is populated, an obvious geometric pattern emerges. Points that land close together share similar traits. A romantic comedy lands right next to other romantic comedies, while action movies occupy a completely different sector. Physical distance reflects similarity. To an artificial intelligence, understanding the meaning of a concept is entirely solved by calculating its physical distance from other concepts in this geometric space. Plotting one or two vectors is straightforward, but a real-world streaming platform analyzes millions of users and thousands of movies simultaneously. Processing that information one point at a time would be too slow to function. To handle that massive scale, engineers stack thousands of these vectors together into a giant rectangular grid. This bulk container of vectors is called a matrix. When you multiply a vector by this matrix grid, it triggers a series of simultaneous dot products. It recalculates every number in the vector, mixing the original features, like age and income, into brand new combinations. This multiplication is the engine that actually manipulates the information. Because the numbers in our vectors have changed, their coordinates on the map must also shift. Multiplying data by a matrix physically stretches, rotates, or squishes the entire coordinate space, pulling overlapping clusters of data apart into clean, separate groups. Every layer in a neural network is a chain of these matrix transformations. As the data passes through each layer, it undergoes successive geometric distortions that continually refine the layout. A neural network learning to recognize patterns is essentially just performing sequential spatial warpings, isolating the exact data the system needs to find. Despite these massive mathematical transformations, real-world data remains messy. AI systems rarely produce absolute 100% certain answers because noise is built into the datasets they learn from. The final layer of a matrix transformation yields a raw numerical score. This represents the network's belief about a specific outcome, like whether an incoming email is spam. To make this score usable, it passes through a mathematical filter. Using a sigmoid function, the raw score slides along a smooth S-shaped curve, mapping it precisely to a value between 0 and 1. This filtered output is a probability distribution. Instead of declaring that an email is spam, the system predicts there is an 82% likelihood that it is spam, based on its location in the final coordinate space. This probabilistic approach allows machines to measure their own uncertainty. If a medical AI calculates a 12% chance of disease, it can flag the case for a human review, rather than making an automated high-stakes decision. This is the three-step ladder of AI, organizing raw data into vectors, bending that space with matrices, and estimating likelihoods through probability. The perceived magic of modern AI is merely an illusion created by the vast, high-speed execution of this simple geometry.